Welcome to this video on total internal reflection and the critical angle. This is a continuation of the geometric optics video on Snell's law and the law of reflection that we talked about in previous videos. So if you haven't watched those, check them out so you know what you're stepping into. Okay, we came up with this law that said the sine of the angle of refraction, that was the angle at which the light bends to when it enters into a new medium, was equal to the ratio of the indices of refraction of the two substances times the sine of the angle of incidence. So basically what it's doing is relating the angle you hit the boundary with to the angle that it bends to on the way out. Now what we see here is when you go from an index of refraction that's less than the index of refraction you're entering, we see that the angle decreases, right? This angle over here. We say that the light actually bends toward the normal, and normal meaning that perpendicular line here, this dashed line. Now, if we go the other way, where we say that N1 is larger than N2, we're going to focus on that in this video. So what I'm going to do here is I'm going to switch the air and the water around. So I'm going to make this water over here, and I'm going to make this air. And what I'm looking to do here, let me stay consistent with the other videos I was using water at 1.333. What I'm doing here is I'm looking at what if you go from a more dense to less dense substance. Well, now we're seeing that the angle is actually increased. So if I turn the angles on here, we see there's an increase. So what we would refer to this as doing is it bends away from the normal. So that's just some of the language, the way we would describe it. Now another thing that's very interesting is going to focus on this idea over here. And this is the what we're focusing on for the remainder of the video, where we're going from a more dense substance. Probably be helpful to write that in here. This is more dense because it's a larger index of refraction. This is less dense. And remember that the index of refraction can never be less than 1. Now here we're approximating air as being a vacuum because we're saying that the speed of the light in the air is the same as the speed of the light in the vacuum. So if you are confused as to what the heck I'm talking about with refractive index and speeds of light, you want to go back and check out the other optics videos to get some of those definitions down. So let's take a look at this. As I increase the angle of incidence now that's in the more dense medium, eventually I reach a point where the angle of refraction actually dropped out. It's not refracting at all. It's completely reflecting. Now the law is still the same for the angle of reflection, so the angle of reflection is exactly the same as the angle of incidence, but the angle of refraction has actually disappeared. Now technically what's actually happening here is once it hits a specific angle of incidence, the angle of refraction is actually going to lie along the boundary, and that's where it technically will disappear. And so what we usually will say here is that the angle of refraction for the critical angle is 90 degrees. So we're going to assume that it's done this, it's gone refracted along the boundary and it's no longer refracting. Okay, so what's essentially happening here is we're saying that the sine of 90 degrees, which is this side of the equation, that's equal to 1. And what we've said now is n1 over n2 is a number now that's actually going to be larger than 1 because this number is bigger up top here than this bottom number. And the sine of the theta of incidence, this one, is going to change to sine sub c, and that is the symbol we're going to use here to represent what we know as the critical angle. This is the angle specifically at which total internal reflection occurs. Now, the reason we call it internal reflection is because, let's say you have your laser underwater and you shine it at the surface of the water. It reaches a specific angle at which it totally reflects back internally into the same substance. So we refer to that as the critical angle. Now, this is still Snell's law. It hasn't changed, but we're setting it up to a specific circumstance. So when we're looking for the critical angle of a substance, what we're referring to is when the angle of refraction is 90 degrees. So that's important to remember. That is implied. So what I can do here is take the original equation, which is this, and this we got from our experiment in the last video. And what we're going to do now is write out some assumptions. So theta refraction, so the refracted angle is, we're assuming, is 90 degrees at the critical angle, and the theta of incidence, this angle over here, is going to be equal to the critical angle at that specific time. Now what we can do then is replace these values. So I'm going to go sine of 90 degrees is equal to n1 over n2 times the sine of the critical angle. Now, if I'm trying to isolate the critical angle, I want to be able to solve for what that is. What I'm going to do here is just move some variables around. So what I'm going to do here is multiply by the reciprocal of this on both sides, and that will get me 1 on this side. Cancel that out. And what I essentially have here is n2 over n1 equals the sine of the critical angle. Now I'll take the inverse sine of both sides, and what I have is the inverse sine of n2 over n1 is equal to the critical angle. So what I'd be able to do here is take any combination of refractive materials and calculate the critical angle for that particular material, meaning the more dense material. But remember, this only functions, this is only true when n2 is less than n1. So n1 has to be bigger in this case, right? So the original material must be larger than the refracted material. Otherwise, you won't be able to have total internal reflection. But it's still a part of the exact same law that we came up with in the first video.